Hey everyone, welcome to the second part of your lesson for today. So the first part we were talking about loop-de-loops, roller coasters, vertical circles. Now we're going to start talking about highway curves, and we're going to kind of dive into a whole different arena for circular motion. Hopefully this one will be pretty relatable too, as most of you drive. So hopefully you'll start secretly thinking about physics when you're just trying to drive. And maybe you don't want to think about physics and it's going to pop into your head. So that's pretty fun. Okay, so what do you feel when driving around a curve? And how can we explain that in terms of circular motion? I'm not talking about emotional feeling here, right? I want to know literally physically, what does your body feel when you're driving around a curve? And if you want, you can think about driving at a faster velocity, slower velocity. But just in general, you're driving around a curve, what kind of happens to your body? So maybe you kind of feel flung outward. What do I mean by outward? I could be a little more specific there. And then the car kind of redirects your motion, right? So depending on which way you're turning, maybe you kind of feel nudged into your car door a little bit. Or maybe if you're turning the other way, you kind of feel flung into the middle of your car. If you've been in the back seat of a crazy driver, you've definitely been flung all over the place, right? So how do we explain that in terms of circular motion? So we're going to delete these so we can see our answer here. Our bodies want to continue motion in a line. When that car starts moving, however, your body wants to keep going like this in a straight line. The car is going to start following a curved path. So you may feel like you're being pushed outwards, but really what you're feeling is the car acting on you to keep you in this circular path. It's going to exert some kind of force, either maybe the friction of the seat or the normal force of the door if you're, kind of being pushed against the door. Maybe pushed against a friend, I don't know. The car is going to kind of correct your body's motion and force your body to follow the curved path. And this is going to be very similar to those rides we were talking about, right? Those circular rides that spin super fast. You feel like you're being flung outwards, but really what you're feeling is your body wanting to continue straight line motion and the ride pushing you back into your circular path. So friction is that centripetal force that causes a car to maintain the curved path. So we're going to be chatting a lot about friction today. But I want you to relate this to real life experience, right? So as you're driving home today, try to make a turn here or there. It doesn't have to be wild and crazy. You can still get this effect even if the turn is a little slower. Or one thing you can do is turn on your AC, like full blast, and then go around a curve. And you'll kind of feel the air current continue on in a straight line, and then I spelled current with 3 R's. You'll feel the air current continue in a straight line, and then it will eventually correct itself. So kind of cool, kind of fun. Try it out. All right, we need to chat a bunch about friction. In this case, sometimes we use a fancy word called traction between a tire and a car. So friction, when we're dealing with highways and highway curves, is super helpful. The friction we talked about before, sometimes it kind of got in the way, right? Like it's preventing motion almost, or it's opposing motion. When we're dealing with highway curves, friction is the thing that's keeping your car on a curve. So super helpful, actually a huge safety factor. So there is static friction between a rolling tire and the road. Why would it be static though, right? I'm moving. Didn't we say kinetic friction is anytime something is in motion? This feels a little bit wrong, but let's try to think through this. If I have a road and I have a wheel, I'm going to have some kind of point of contact. So this point of contact here, it doesn't slide down the road. It doesn't skid, hopefully. If it was sliding, then you would have kinetic friction. But what happens is I have a point of contact, but then my tire rotates, and so then I have another point of contact, and another point of contact, another point of contact. So what we're looking at is this instant of contact with a point on the tire and the road, and that contact, the force that's felt there, it's static friction, okay? Because it's kind of like this instantaneous thing almost. So yes, your wheel is rolling. If you are skidding, then it would be kinetic friction. But if your tire is rolling properly the way it should, the friction we're analyzing is actually static friction. If the car skids or if the brakes lock, causing the car to slide, anytime your tire is literally sliding down the road like that, then we're looking at kinetic friction. Kinetic friction tends to be a lot weaker than static friction. So this is where it gets a little unsafe, right? And you know this intuitively. it's not very safe to be skidding down a road. That's not a good thing, right? Kinetic friction can't hold your car on the road as well as static friction can. So as a car drives around a curve, friction keeps it on the curved path, and your static friction here acts perpendicular to velocity. So if you think about kind of a top-down view, here's my curve, here's my car, your force of friction is going to act like this. Your velocity, right, is just this straight line vector. Your force of friction is keeping you on the road. If you're looking at your car from the front, this is the front view, this is the top-down view, friction would be keeping you on the road. And then what other forces do we have at play? Well, you have weight, mass times gravity, and you're going to have normal force. All right, so might be drawing some FBDs in this section. Get excited. If the car skids, the kinetic friction opposes velocity. So that's where friction goes back to being kind of more harmful than helpful. And there's no force keeping the car on the curve. So kinetic friction when driving is not good. Static friction is the thing that we want. We want the car tires to just be rolling properly. This is why icy conditions can be a lot less safe, because it reduces the strength of static friction between your car tires and the road. So let's do a problem about that. Example 4. I have a car. It's 1,000 kilograms. It rounds a curve on a flat road, so this curve isn't banked, or we'll talk about that in a second. It's not tipped or tilted. I'm not going uphill or downhill, just on a flat road, and there's a curve. So it's going to kind of look like this. Here's my little car tootling along. You're going to have a force of friction keeping you on that curved path. If there was no force, your car would just want to go in a straight line. This friction will kind of keep you on this curve. We like that. We want that. If you look at this car from the side, or sorry, the front, this is my front view now. I have weight, mass times gravity acting downwards. I have normal force acting upwards. I have a force of friction acting to the side, kind of perpendicular to both of those. So there's your little FBD for this. Okay, so I'm on a curve, flat road. The curve radius is 50 meters. And I know my velocity is 14 meters per second. Will the car follow the curve, or will it skid? So we're going to have two different cases here. One, we're going to assume the pavement is dry, and our coefficient of static friction is 0.60. And case B, it's going to be icy. My static coefficient of friction is going to be less. Static friction is not going to be quite as strong. So what we basically want to do in this problem is we want to compare the centripetal force that's going to be acting on this thing, right, based on mass, velocity, and our radius of curvature. We want to compare that with the friction that this car has based on your coefficient of friction. Okay, so compare force of friction with force needed to provide centripetal acceleration. Okay, so FC equals mv squared r. This is what we would need to keep us on the curve. You know mv and r, so go ahead and plug those in. I have 1,000 kilograms times the velocity we're going is 14 meters per second squared over r, that's 50 meters. If you plug that all into your calculator, you're going to get 3,920 newtons. So that's the necessary centripetal force to keep us on this curve. Let's check our friction force and see, is it at least 3,920 newtons? If it is, then cool, friction's going to keep me on the road. I will follow the curve. If it's less than that, then crap, I'm going to skid, okay? So remember our friction equation. Do we remember it? It's mu times normal force. I know what mu is. What would your normal force be for this problem? So hopefully my car isn't like rising above the ground or sinking. So in this case, normal force and weight, they're just going to be balanced. So here I'm plugging in mu times mg. That would be 0.6. Our mass is 1,000 kilograms. G is 10 meters per second squared. When you plug those all into your calculator, you're going to get 6,000 newtons. So because this force, the force of friction, is greater than the needed or required centripetal force to keep us on the curve, yep, the car will follow the curve. And that's good. That's what we want. So because, again, friction is greater than needed centripetal force. What about part B? Our necessary centripetal force is the same, right? So I'm now just checking my force of friction if conditions are icy. So that's going to be 0.25 times, my normal force here was 1,000 times 10, so 0.25 times 10,000 newtons. When I multiply that out, I'm going to get 2,500 newtons. Because this is less than the needed centripetal force, the car will skid. I don't have enough friction to keep me on that curved path, okay? So this is literally the physics behind why icy roads and curves are more dangerous. This is why your car sometimes will skid when you're going around a curve. It's why curves are more dangerous, especially in icy conditions. So think about some of this stuff. Don't experiment too much on the roads. But now you kind of know how to explain that. That's actually really, really awesome. Okay, here's where we step it up a notch. Get ready, everyone. What if I have a banked curve? So banking curves, basically it means tipping a curve reduces skidding. Think about all the forces acting on a car traveling around a banked curve. Why would a slight bank prevent skidding? So I'm going to be drawing this from the side here. Picture your curve. I'm looking at a car kind of straight on right now. Here's my car. Okay. And you've driven on banked curves before. I can guarantee you that you have. A lot of highway exits, they'll have a kind of tilt to them, a kind of tip. It's for safety reasons. It's to make sure that you stay on the road. So when you're driving on and off the highway, start paying attention to the curve and see if it's banking in the right direction or not. I can tell you of specific examples in northern Jersey where the civil engineers kind of screwed up a little bit and they tipped it the wrong direction. So we'll chat about those. Okay, so here's my curve. This is my front view of the car. Okay, instead of just being flat, now I'm up at some kind of angle. There's some kind of banking angle here. Let's think about the forces at play. Well, I have weight. Remember, weight is always just going to point directly down. You have normal force. That's pointing like this. In this case, because normal force is up at an angle, the normal force, I'm going to write this out. This is really, really important. The normal force contributes to the sum of your centripetal forces. So stick with me on this, folks. If you consider X and Y here, X and Y axes, you would have components, right? You would have an X component of normal force. You would have a Y component of normal force. If you know the angle, the banking angle down here, we could go through the geometry of it all, but this angle would be the same as this angle up here, okay? So that means that over here you would have Fn sine theta and Fn cosine theta for your different components. This kind of goes back to weight. Remember how for weight, the X and Y components kind of flipped with the sine and cosine? That's basically what's going on here. Okay. Once again, if you need to pause the video, you need to figure out your triangles. You need to reason through why those angles are the same. Do it. Your textbook also explains it a little bit more. So read through this section in the textbook. Ask me questions when I come back next week. We can figure that out. Or you can just trust, sweet, if I know my banking angle, I know it's this, and I know to find my components of normal force. Your X component is Fn sine theta. Your Y component is Fn cosine theta. Do what's going to help you. Okay. My centripetal acceleration should be in this direction because I hopefully stay on the curve. So hopefully when you're going around a curve, you're kind of tipped in towards the curve. And again, the goal of this is so normal force contributes to the sum of your centripetal forces. Okay. So here's a special equation for us. There is a component of the normal force that points towards the circle center, reducing the need for friction. This is how engineers design roads. There is an angle for which a car needs no friction, and that's a good thing to maintain the curved path. So engineers can design roads so that you're not relying on friction, on static friction or kinetic friction, anything. You're not relying on friction to keep your car on the road. You're totally relying on a component of normal force. So our version of the equation for this would be Fn sine theta, that x component equals mv squared over r. When this is the case, no friction is required to keep the car on the curve. And once again, that's really, really good, right? I don't want to have some component of friction over there. I don't want that. I don't need that. I just want normal force to keep me on that curve, okay? So we are going to do a problem with this, all right? Stick with me, folks. You got this. You've kind of done stuff similar to this. It's just it's a new way of thinking of it, okay? So I have a car traveling with speed v around curve of radius r. I want to determine the formula for the angle at which the road should be banked to eliminate the need for friction. Once we go through this derivation, you can just have this formula and use this formula and know that this will work for whatever v and r you have, okay? I am making you go through the derivation. It's part of the process. I want you to understand where this formula is coming from, okay? So we're going to have a pretty similar diagram to the one I drew on a previous page. Here's my car. It's at this banked angle. I have weight acting downwards. I have normal force acting kind of to the side. I'm going to split this up into x and y components. I know that this angle over here is also theta. When I separate this out, I'm going to get Fn sine theta. Over here, I'm going to get Fn cosine theta. And we're good to go. So we're going to use our centripetal force equation. That's what we're going to start with for this derivation. I'm writing it like this just to once again remind us it's F equals ma, okay? Now I'm going to replace this on my centripetal forces with just Fn sine theta. This is the only force acting towards the center of my circle, so it's the only contributing force for centripetal force. I know centripetal acceleration is v squared over r. Okay, beautiful. Hopefully I have no vertical motion. So what I mean by that is my car isn't like sinking into the ground or rising up. So I should be able to say that Fn cosine theta equals mass times gravity, okay? When I'm finding Fn, then I can say that Fn equals mg over cosine theta, right? All I did was divide out by cosine theta for this equation over here. Now I have a beautiful expression for normal force that I can go ahead and plug into my earlier equation. So I have mg cosine theta, that's an expression for normal force, times sine theta, equals mv squared over r. Let's simplify a little bit. I have m on both sides, so once again, I don't care what the mass is. I could have an 18-wheeler that's thousands of pounds. I could have a tiny little car, right? I don't really care what the mass is, but I do care about the velocity. I do care about the radius of curvature. So v and r are important. Mass is not super important. Over here, I have g times sine theta over cosine. Well, sine theta over cosine theta, I can condense that, right? That's going to be tan theta. Over here, I have v squared over r. I want to get tan theta by itself or even just theta by itself. So I'm going to divide everything by g. You're left with this equation. Tan theta equals v squared over r times g. And if you want to just find theta, all you have to do is take the inverse tangent. Okay, v squared over rg. All right. So you are welcome to just keep these equations in either this form or this form. Use these anytime a problem is asking you for a banking angle, okay? This is the theta value that will allow you to design a road, a curve that doesn't require friction to keep a car on the road, okay? We're going to use this real quick. We're going to use this equation. Theta equals inverse tan of v squared over rg. In a problem, here I have r, here I have a v. theta equals inverse tangent of 14 meters per second squared over my radius of curvature, r, times g, which is just positive 10 meters per second squared. Plug that all into your calculator. You're going to get theta equals about 21 degrees. Okay, so this is used when people are designing roads to try to figure out how you should bank a certain angle to make sure it's safe for people. I can point out two highway exits. If you get off exit, I think it's 52, heading from, oh crap, what are the highways? If you're going from 208, no, 287. Okay, if you're going from 287 to 23 and you take exit 52, terrible curve, terribly banked. It's banked in the wrong direction. Or if you go from Route 4 to 17, one of those exits there, like if you're by the Garden State Plaza Mall, if you're over there, one of those exits, it's like a little rough. I feel like they kind of banked it the wrong way too. So anyway, let me know if you have other curves in mind that are banked correctly or incorrectly. This has been a lot. Use these days however you need to use them. If you need to split stuff up, do so. You got this. Email me with questions. Look stuff up. Have a little fun with this too. Yes, there are a lot of equations. I believe in you. Bye.